Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You work for a social media company. You need to detect whether posted images contain cars. Each training example is a member of exactly one class. You have trained an object detection neural network and deployed the model version to AI platform prediction for evaluation. Before deployment, you created an evaluation job and attached it to the AI platform prediction model version. You notice that the precision is lower than your business requirements allow. How should you adjust the model's final layer softmax threshold to increase precision? The options are: Option A, increase the recall. Option B, decrease the recall. Option C, increase the number of false positives. Option D, decrease the number of false negatives.
To arrive at the correct answer, we focus on the keywords: precision is lower, adjust the model's final layer softmax threshold to increase precision.
The correct answer is option B, decrease the recall.
Why is this correct? B. Raising the classification threshold makes the model more conservative, which increases precision by reducing false positives. However, this trade-off inherently decreases recall by also reducing true positives and increasing false negatives. Why are the others incorrect? A. Increasing recall requires lowering the threshold, which would increase false positives and thereby decrease precision, opposite to the stated goal. C. To increase precision, you must decrease the number of false positives, not increase them. Increasing false positives lowers precision. D. Increasing precision by raising the classification threshold leads to an increase in false negatives, not a decrease.
You work for a company that is developing a new video streaming platform. You have been asked to create a recommendation system that will suggest the next video for a user to watch. After a review by an AI ethics team, you are approved to start development. Each video asset in your company's catalog has useful metadata, e.g., content type, release date, country, but you do not have any historical user event data. How should you build the recommendation system for the first version of the product? The options are: Option A, launch the product without machine learning. Present videos to users alphabetically, and start collecting user event data so you can develop a recommender model in the future. Option B, launch the product without machine learning. Use simple heuristics based on content metadata to recommend similar videos to users, and start collecting user event data so you can develop a recommender model in the future. Option C, launch the product with machine learning. Use a publicly available dataset such as MovieLens to train a model using the recommendations AI, and then apply this trained model to your data. Option D, launch the product with machine learning. Generate embeddings for each video by training an autoencoder on the content metadata using TensorFlow. Cluster content based on the similarity of these embeddings, and then recommend videos from the same cluster.
To arrive at the correct answer, we focus on the keywords: useful metadata, do not have any historical user event data, first version of the product.
The correct answer is option B, launch the product without machine learning. Use simple heuristics based on content metadata to recommend similar videos to users, and start collecting user event data so you can develop a recommender model in the future.
Why is this correct? B. Without historical user data, using simple heuristics on available metadata is the best approach for a first version to handle the cold start problem while collecting data for future ML models. Why are the others incorrect? A. Presenting videos alphabetically provides a poor user experience because it completely ignores the available useful metadata that could provide relevant recommendations. C. Public datasets like MovieLens have completely different items and user bases, making a model trained on them irrelevant and ineffective for your specific video catalog. D. Building an autoencoder and clustering system based only on metadata is overly complex for a first version and unlikely to significantly outperform simple heuristic rules.
You are building a predictive maintenance model to preemptively detect part defects in bridges. You plan to use high-definition images of the bridges as model inputs. You need to explain the output of the model to the relevant stakeholders so they can take appropriate action. How should you build the model? The options are: Option A, use scikit-learn to build a tree-based model and use SHAP values to explain the model output. Option B, use scikit-learn to build a tree-based model and use partial dependence plots, PDP, to explain the model output. Option C, use TensorFlow to create a deep learning-based model and use integrated gradients to explain the model output. Option D, use TensorFlow to create a deep learning-based model and use the sampled Shapley method to explain the model output.
To arrive at the correct answer, we focus on the keywords, high-definition images, explain the output of the model.
The correct answer is option C, use TensorFlow to create a deep learning-based model, and use integrated gradients to explain the model output.
Why is this correct? C. TensorFlow's deep learning models are ideal for high-definition images. Integrated gradients is specifically designed and recommended for explaining differentiable deep learning models, particularly for attributing predictions to input features like image pixels. Why are the others incorrect? A. Tree-based models in scikit-learn are suited for tabular data and perform poorly on raw high-definition image inputs compared to deep learning approaches. B. Tree-based models are inadequate for image data, and partial dependence plots are used for interpreting tabular features rather than pixel-level data. D. While TensorFlow is correct for images, sampled Shapley is typically used for non-differentiable models or tabular data. Integrated gradients is the appropriate and efficient method for deep learning image classifiers.
Refer to the attached Picture 1, reference exhibit. Your team is working on an NLP research project to predict political affiliation of authors based on articles they have written. You have a large training dataset that is structured like this. You followed the standard 80%-10%-10% data distribution across the training, testing, and evaluation subsets. How should you distribute the training examples across the train test eval subsets while maintaining the October 10th, 80 proportion? The options are: Option A, distribute texts randomly across the train test eval subsets, train set, text A1, text B2, test set, text A2, text C1, text D2, eval set, text B1, text C2, text D1. Option B, distribute authors randomly across the train test eval subsets, asterisk, train set, text A1, text A2, text D1, text D2, test set, text B1, text B2, eval set, text C1, text C2. Option C, distribute sentences randomly across the train test eval subsets, train set, sentence A11, sentence A21, sentence B11, sentence B21, sentence C11, sentence 21, test set, sentence A12, sentence A22, sentence B12, sentence C22, sentence C12, sentence 22, eval set, sentence A13, sentence A23, sentence B13, sentence C23, sentence C13, sentence 31. Option D, distribute paragraphs of texts, i.e., chunks of consecutive sentences, across the train test eval subsets, train set, sentence A11, sentence A12, sentence 11, sentence 12, test set, sentence A13, sentence B13, sentence B21, sentence 23, sentence C12, sentence 13, eval set, sentence A11, sentence A22, sentence B13, sentence 22, sentence C23, sentence 11.
To arrive at the correct answer, we focus on the keywords, predict political affiliation of authors based on articles they have written.
The correct answer is option B, Distribute authors randomly across the train test eval subsets, train set, text A1, text A2, text D1, text D2, test set, text B1, text B2, eval set, text C1, text C2.
Why is this correct? B. Splitting the dataset by authors prevents data leakage. If texts from the same author exist in both training and evaluation sets, the model may memorize the author's specific writing style instead of learning generalizable patterns for political affiliation. Why are the others incorrect? A. Randomly distributing texts causes data leakage. Multiple texts from the same author will appear in both training and testing sets, causing the model to overfit on author-specific writing styles rather than true political affiliations. C. Distributing sentences randomly introduces severe data leakage. Sentences from the same text and author will appear across sets, allowing the model to memorize specific text structures instead of generalizing to political affiliation. D. Splitting by paragraphs causes data leakage. Paragraphs from the identical text and author will be distributed across all sets, resulting in an invalid evaluation since the model has already seen the author's style during training.
You work for a pet food company that manages an online forum. Customers upload photos of their pets on the forum to share with others. About 20 photos are uploaded daily. You want to automatically and in near real time detect whether each uploaded photo has an animal. You want to prioritize time and minimize cost of your application development and deployment. What should you do? The options are: Option A, send user-submitted images to the Cloud Vision API. Use object localization to identify all objects in the image and compare the results against a list of animals. Option B, download an object detection model from TensorFlow Hub. Deploy the model to a Vertex AI endpoint. Send new user-submitted images to the model endpoint to classify whether each photo has an animal. Option C, manually label previously submitted images with bounding boxes around any animals. Build an AutoML object detection model by using Vertex AI. Deploy the model to a Vertex AI endpoint. Send new user-submitted images to your model endpoint to detect whether each photo has an animal. Option D, manually label previously submitted images as having animals or not. Create an image dataset on Vertex AI. Train a classification model by using Vertex AutoML to distinguish the two classes. Deploy the model to a Vertex AI endpoint. Send new user-submitted images to your model endpoint to classify whether each photo has an animal.
To arrive at the correct answer, we focus on the keywords, automatically and in near real time, detect whether each uploaded photo has an animal, prioritize time and minimize cost of your application development and deployment.
The correct answer is option A, send user-submitted images to the Cloud Vision API. Use object localization to identify all objects in the image and compare the results against a list of animals.
Why is this correct? A. The Cloud Vision API provides a pre-trained, ready-to-use solution for object localization, requiring minimal development time and operational overhead. This perfectly aligns with the goal to prioritize time and minimize cost. Why are the others incorrect? B. Deploying a model from TensorFlow Hub requires setting up endpoints and infrastructure, increasing development time and operational costs compared to using a fully managed pre-trained API. C. Manually labeling images in training an AutoML model is time-consuming and incurs training and deployment costs, contradicting the requirement to minimize cost and prioritize development time. D. Manually labeling data and training a custom AutoML classification model requires significant development time and higher costs than using a pre-trained API, making it suboptimal.
You recently trained a XGBoost model that you plan to deploy to production for online inference. Before sending a predict request to your model's binary, you need to perform a simple data pre-processing step. This step exposes a REST API that accepts requests in your internal VPC service controls and returns predictions. You want to configure this pre-processing step while minimizing cost and effort. What should you do? The options are: Option A, store a pickled model in cloud storage. Build a Flask-based app, package the app in a custom container image, and deploy the model to Vertex AI endpoints. Option B, build a Flask-based app, package the app and a pickled model in a custom container image, and deploy the model to Vertex AI endpoints. Option C, build a custom predictor class based on XGBoost predictor from the Vertex AI SDK, package it and a pickled model in a custom container image based on a Vertex built-in image, and deploy the model to Vertex AI endpoints. Option D, build a custom predictor class based on XGBoost predictor from the Vertex AI SDK, and package the handler in a custom container image based on a Vertex built-in container image. Store a pickled model in cloud storage, and deploy the model to Vertex AI endpoints.
To arrive at the correct answer, we focus on the keywords: XGBoost model, deploy to production for online inference, simple data pre-processing step, minimizing cost and effort.
The correct answer is option D, build a custom predictor class based on XGBoost predictor from the Vertex AI SDK, and package the handler in a custom container image based on a Vertex built-in container image. Store a pickled model in cloud storage, and deploy the model to Vertex AI endpoints.
Why is this correct? D. Creating a custom predictor class based on XGBoost predictor minimizes effort by leveraging custom prediction routines, CPR, on top of built-in containers. Storing the pickled model in cloud storage correctly separates the model artifact from the serving image, following best practices. Why are the others incorrect? A. Building a custom Flask-based app from scratch requires significantly more effort and development time than extending a built-in Vertex AI container using custom prediction routines, CPR. B. Packaging the model inside the container image is an anti-pattern that requires rebuilding the image for every model update. Furthermore, building a Flask app from scratch maximizes rather than minimizes effort. Why are the others incorrect? C. Packaging the pickled model directly in the custom container image is an anti-pattern. Model artifacts should be stored separately in cloud storage so you can deploy new model versions without rebuilding the container.
You work at a leading healthcare firm developing state-of-the-art algorithms for various use cases. You have unstructured textual data with custom labels. You need to extract and classify various medical phrases with these labels. What should you do? The options are: Option A, use the Healthcare Natural Language API to extract medical entities. Option B, use a BERT-based model to fine-tune a medical entity extraction model. Option C, use AutoML entity extraction to train a medical entity extraction model. Option D, use TensorFlow to build a custom medical entity extraction model.
To arrive at the correct answer, we focus on the keywords: unstructured textual data with custom labels, extract and classify various medical phrases with these labels.
The correct answer is option C, use AutoML entity extraction to train a medical entity extraction model.
Why is this correct? C. AutoML entity extraction is designed to train custom entity extraction models using custom labeled unstructured text, offering an efficient managed solution without requiring extensive ML coding. Why are the others incorrect? A. The Healthcare Natural Language API is pre-trained to extract standard medical entities and does not support training models to extract custom labels. B. Fine-tuning a BERT-based model requires significant ML expertise, coding effort, and infrastructure, making it less efficient than using a managed service like AutoML. D. Building a custom TensorFlow model from scratch requires substantial machine learning expertise and development time, whereas AutoML provides a more practical and streamlined solution.
You are developing a TensorFlow extended (TFX) pipeline with standard TFX components. The pipeline includes data pre-processing steps. After the pipeline is deployed to production, it will process up to 100 terabytes of data stored in BigQuery. You need the data pre-processing steps to scale efficiently, publish metrics and parameters to Vertex AI experiments, and track artifacts by using Vertex ML metadata. How should you configure the pipeline run? The options are: Option A, run the TFX pipeline in Vertex AI pipelines. Configure the pipeline to use Vertex AI training jobs with distributed processing. Option B, run the TFX pipeline in Vertex AI pipelines. Set the appropriate Apache Beam parameters in the pipeline to run the data pre-processing steps in Dataflow. Option C, run the TFX pipeline in Dataproc by using the Apache Beam TFX orchestrator. Set the appropriate Vertex AI permissions in the job to publish metadata in Vertex AI. Option D, run the TFX pipeline in Dataflow by using the Apache Beam TFX orchestrator. Set the appropriate Vertex AI permissions in the job to publish metadata in Vertex AI.
To arrive at the correct answer, we focus on the keywords TensorFlow Extended, TFX, Pipeline, Data Preprocessing Steps, Scale Efficiently, Publish Metrics and Parameters to Vertex AI Experiments, Track Artifacts by using Vertex ML metadata.
Correct answer is option B, run the TFX pipeline in Vertex AI pipelines. Set the appropriate Apache Beam parameters in the pipeline to run the data preprocessing steps in Dataflow.
Why is this correct? B. Vertex AI pipelines natively integrates with Vertex ML metadata and experiments. TFX uses Apache Beam for data processing components. Configuring Beam parameters to use Dataflow ensures data preprocessing scales efficiently to handle 100 terabytes of data. Why are the others incorrect? A. Vertex AI training is designed for training ML models, not for distributed data preprocessing tasks, which are handled by Apache Beam and TFX. C. Dataproc and the Apache Beam orchestrator lack native, out-of-the-box integration with Vertex AI experiments and ML metadata, requiring complex custom implementations. D. Using the Apache Beam TFX orchestrator on Dataflow does not provide the built-in tracking for Vertex ML metadata and experiments that Vertex AI pipelines offers natively.
You are developing a model to help your company create more targeted online advertising campaigns. You need to create a dataset that you will use to train the model. You want to avoid creating or reinforcing unfair bias in the model. What should you do? Choose 2. The options are: Option A, include a comprehensive set of demographic features. Option B, include only the demographic groups that most frequently interact with advertisements. Option C, collect a random sample of production traffic to build the training dataset. Option D, collect a stratified sample of production traffic to build the training dataset. Option E, conduct fairness tests across sensitive categories and demographics on the trained model.
To arrive at the correct answer, we focus on the keywords create a dataset, avoid creating or reinforcing unfair bias.
The correct answer is option D, collect a stratified sample of production traffic to build the training dataset.
Why is this correct? D. Stratified sampling ensures that minority and underrepresented groups are proportionally included in the training dataset, which effectively prevents representation bias. Why are the others incorrect? A. Including comprehensive demographic features can cause the model to learn discriminatory patterns and amplify existing biases based on sensitive attributes. B. Including only groups that interact frequently exacerbates bias by completely omitting underrepresented demographics from the training data. C. Random sampling from production traffic typically underrepresents minority groups, leading to imbalanced data and representation bias. E. While fairness testing is crucial, it evaluates the trained model rather than addressing the immediate task of creating an unbiased training dataset.
You have been tasked with deploying prototype code to production. The feature engineering code is in PySpark and runs on Dataproc serverless. The model training is executed by using a Vertex AI custom training job. The 2 steps are not connected, and the model training must currently be run manually after the feature engineering step finishes. You need to create a scalable and maintainable production process that runs end-to-end and tracks the connections between steps. What should you do? The options are: Option A, create a Vertex AI Workbench notebook. Use the notebook to submit the Dataproc serverless feature engineering job. Use the same notebook to submit the custom model training job. Run the notebook cells sequentially to tie the steps together end-to-end. Option B, create a Vertex AI Workbench notebook. Initiate an Apache Spark context in the notebook and run the PySpark feature engineering code. Use the same notebook to run the custom model training job in TensorFlow. Run the notebook cells sequentially to tie the steps together end-to-end. Option C, use the Kubeflow Pipelines SDK to write code that specifies two components. The first is a Dataproc serverless component that launches the feature engineering job. The second is a custom component wrapped in the create_custom_training_job_from_component utility that launches the custom model training job. Create a Vertex AI Pipelines job to link and run both components. And the remaining options are: Option D, use the Kubeflow Pipelines SDK to write code that specifies two components. The first component initiates an Apache Spark context that runs the PySpark feature engineering code. The second component runs the TensorFlow custom model training code. Create a Vertex AI Pipelines job to link and run both components.
To arrive at the correct answer, we focus on the keywords: deploying prototype code to production, runs on Dataproc serverless, Vertex AI custom training job, scalable and maintainable production process, tracks the connections between steps.
The correct answer is option C. Use the Kubeflow Pipelines SDK to write code that specifies two components. The first is a Dataproc serverless component that launches the feature engineering job. The second is a custom component wrapped in the create_custom_training_job_from_component utility that launches the custom model training job. Create a Vertex AI Pipelines job to link and run both components. Review the options on screen.
Why is this correct? C. Vertex AI Pipelines provides a scalable, maintainable production process with built-in artifact tracking. Using Kubeflow Pipelines SDK components for Dataproc serverless and Vertex AI custom training efficiently orchestrates the existing jobs without rewriting them. Why are the others incorrect? A. Running notebook cells sequentially is suitable for prototyping but is not a robust, scalable, or maintainable production process. It lacks built-in mechanisms for automated orchestration, retry logic, and tracking connections between steps. B. Executing PySpark and TensorFlow directly in a notebook is an interactive development pattern, not a production-ready, scalable process. It fails to utilize the specified Dataproc serverless and Vertex AI custom training services. D. Initiating Spark and TensorFlow directly within pipeline components runs heavy workloads inside orchestrator pods. This is unscalable and ignores the requirement to use the existing Dataproc serverless and Vertex AI custom training services.
You work for an online grocery store. You recently developed a custom ML model that recommends a recipe when a user arrives at the website. You chose the machine type on the Vertex AI endpoint to optimize costs by using the queries per second (QPS) that the model can serve, and you deployed it on a single machine with 8 vCPUs and no accelerators. A holiday season is approaching and you anticipate 4 times more traffic during this time than the typical daily traffic. You need to ensure that the model can scale efficiently to the increased demand. What should you do? The options are: Option A, 1. Maintain the same machine type on the endpoint. Point 2. Set up a monitoring job and an alert for CPU usage. Point 3. If you receive an alert, add a compute node to the endpoint. Option B, 1. Change the machine type on the endpoint to have 32 vCPUs. Point 2. Set up a monitoring job and an alert for CPU usage. Point 3. If you receive an alert, scale the vCPUs further as needed. Option C, 1. Maintain the same machine type on the endpoint. Configure the endpoint to enable autoscaling based on vCPU usage. Point 2. Set up a monitoring job and an alert for CPU usage. Point 3. If you receive an alert, investigate the cause. Option D. 1. Change the machine type on the endpoint to have a GPU. Configure the endpoint to enable autoscaling based on the GPU usage. Point 2. Set up a monitoring job and an alert for GPU usage. Point 3. If you receive an alert, investigate the cause.
To arrive at the correct answer, we focus on the keywords Vertex AI endpoint, optimize costs, 8 vCPUs, and no accelerators, scale efficiently.
The correct answer is option C. 1. Maintain the same machine type on the endpoint. Configure the endpoint to enable autoscaling based on vCPU usage. Point 2. Set up a monitoring job and an alert for CPU usage. Point 3. If you receive an alert, investigate the cause.
Why is this correct? C. Vertex AI endpoints support autoscaling based on vCPU utilization. This efficiently handles the anticipated traffic spikes by automatically adding or removing compute nodes as needed, ensuring high availability while maintaining cost optimization. Why are the others incorrect? A. Relying on manual intervention, adding nodes after receiving an alert, is inefficient, not scalable, and can result in significant latency or dropped requests during traffic spikes. B. Manually changing to a larger static machine type, vertical scaling, is less cost-effective, as you pay for unused peak capacity during normal traffic periods. D. The model was already deployed and optimized for a machine with no accelerators. Switching to GPUs would unnecessarily increase costs and might require model changes.
You are an ML engineer at a mobile gaming company. A data scientist on your team recently trained a TensorFlow model, and you are responsible for deploying this model into a mobile application. You discover that the inference latency of the current model doesn't meet production requirements. You need to reduce the inference time by 50%, and you are willing to accept a small decrease in model accuracy in order to reach the latency requirement. Without training a new model, which model optimization technique for reducing latency should you try first? The options are Option A, weight pruning. Option B, dynamic range quantization. Option C, model distillation. Option D, dimensionality reduction.
To arrive at the correct answer, we focus on the keywords mobile application, reduce the inference time, without training a new model.
Correct answer is option B, dynamic range quantization.
Why is this correct? B. Dynamic range quantization is a post-training technique that reduces model size and latency by converting floating point weights to lower precision without requiring model retraining, making it ideal for mobile deployments. Why are the others incorrect? A. Weight pruning removes less important model weights, but it typically requires retraining or fine-tuning the model to recover the lost accuracy. C. Model distillation involves training a new, smaller student model to mimic the behavior of a larger teacher model, violating the constraint of not training a new model. D. Dimensionality reduction is applied to feature engineering before training or requires modifying the model architecture and retraining, violating the requirement to not train a new model.
You work for an auto insurance company. You are preparing a proof-of-concept ML application that uses images of damaged vehicles to infer damaged parts. Your team has assembled a set of annotated images from damage claim documents in the company's database. The annotations associated with each image consist of a bounding box for each identified damaged part and the part name. You have been given a sufficient budget to train models on Google Cloud. You need to quickly create an initial model. What should you do? The options are Option A, download a pre-trained object detection model from TensorFlow Hub. Fine-tune the model in Vertex AI Workbench by using the annotated image data. Option B, train an object detection model in AutoML by using the annotated image data. Option C, create a pipeline in Vertex AI Pipelines and configure the AutoML training job runOp component to train a custom object detection model by using the annotated image data. Option D, train an object detection model in Vertex AI custom training by using the annotated image data.
To arrive at the correct answer, we focus on the keywords, proof of concept, bounding box for each identified damaged part, quickly create an initial model.
The correct answer is option B, train an object detection model in AutoML by using the annotated image data.
Why is this correct? B. AutoML is the recommended Google Cloud service to quickly build and deploy high-quality custom machine learning models with minimal effort, making it ideal for an initial proof of concept. Why are the others incorrect? A. Manually fine-tuning a model in Workbench requires writing custom training code and managing the environment, which is slower and more complex than using AutoML. C. Building a Vertex AI pipeline adds unnecessary engineering complexity and overhead that is not needed for simply and quickly training an initial proof-of-concept model. D. Custom training requires developing, debugging, and managing your own training scripts, which contradicts the goal of quickly creating an initial model when AutoML is available.
You have deployed a Scikit-team model to a Vertex AI endpoint using a custom model server. You enabled autoscaling, however, the deployed model fails to scale beyond one replica, which led to dropped requests. You notice that CPU utilization remains low even during periods of high load. What should you do? The options are: Option A, attach a GPU to the prediction nodes. Option B, increase the number of workers in your model server. Option C, schedule scaling of the nodes to match expected demand. Option D, increase the min replica count in your deployed model configuration.
To arrive at the correct answer, we focus on the keywords, custom model server, fails to scale beyond one replica, CPU utilization remains low, periods of high load.
The correct answer is option B, increase the number of workers in your model server.
Why is this correct? B. A custom model server might be single-threaded by default, processing requests sequentially. This keeps CPU usage low, preventing CPU-based autoscaling. Increasing the number of workers allows concurrent request processing, raising CPU utilization and successfully triggering autoscaling. Why are the others incorrect? A. Scikit-learn models do not typically benefit from GPUs during inference, so this would not address the issue of low CPU utilization and dropped requests. C. Scheduled scaling provisions nodes at specific times but does not fix the root cause, the server's inability to process concurrent requests and trigger the already enabled autoscaling. D. Increasing min replica count adds static capacity but does not resolve the underlying issue of the single replica failing to utilize CPU and trigger dynamic autoscaling.
You are developing an ML model to identify your company's products in images. You have access to over 1 million images in a cloud storage bucket. You plan to experiment with different TensorFlow models by using Vertex AI training. You need to read images at scale during training while minimizing data I/O bottlenecks. What should you do? The options are: Option A, load the images directly into the Vertex AI compute nodes by using Cloud Storage Fuse. Read the images by using the tf.data, dataset.from_tensor_slices function. Option B, create a Vertex AI managed dataset from your image data. Access the AIP_training_data_URI environment variable to read the images by using the tf.data, dataset.list_files function. Option C, convert the images to TF records and store them in a cloud storage bucket. Read the TF records by using the tf.data.tfRecordDataset function. Option D, store the URLs of the images in a CSV file. Read the file by using the tf.data.experimental.csvDataset function.
To arrive at the correct answer, we focus on the keywords, over 1 million images, TensorFlow models, read images at scale, minimizing data I/O bottlenecks.
The correct answer is option C, convert the images to TF records and store them in a cloud storage bucket. Read the TF records by using the tf.data.tfRecord dataset function.
Why is this correct? C. TF records format is native to TensorFlow and optimizes data reading by grouping multiple files into larger chunks, significantly reducing data I/O bottlenecks when reading millions of images at scale. Why are the others incorrect? A. Cloud storage fuse and tf.data dataset.from_tensor_slices are inefficient for reading over a million individual image files, leading to high latency and severe data I/O bottlenecks. B. While Vertex AI datasets are useful, reading millions of separate image files using tf.data dataset.list_files still incurs high I/O latency and fails to minimize data I/O bottlenecks effectively. D. tf.data.experimental.csv dataset reads text/CSV data. Downloading millions of individual images from URLs during training would introduce massive latency and fail to minimize data I/O bottlenecks.